okay, we are going to go into lecture 2. Okay, from my part, is going to be divided into 2, which is going to be enthalpy change of solution, enthalpy change of hydration, and after 30 minutes, okay, hopefully we will be able to start with our entropy. Okay, so 30 minutes and 30 minutes. This lesson is designed as a review. So if you feel that it's too fast and so on, go ahead to go to my Google site. And then there is a full lesson, okay, on this enthalpy change of solution, hydration, and also full lesson on this entropy. So I will just do a review for those who have not learned with your teachers. Okay, you can actually go and look at those lectures. Yeah. So now the first thing that I want to actually teach you over here is, okay, enthalpy changes in solution. As usual, okay, you need to know what is going to be the definition of enthalpy changes in solution. It's written over there. The energy absorbed or released, okay, when 1 mole of ionic solid dissolved in sufficient water to form a very dilute solution. So from here, okay, if you look at absorb and release, okay, it means that it can be both. Okay, it can be both positive or negative. It can be endothermic. It can be also exothermic. So how do we write equations when it comes to enthalpy changes in solution? The equation is going to be 1 mole of ionic solid. So NaCl, for example, solid. When I add with water, I'll write it down as AQ. And I am going to get NaCl aqueous solution. Okay, some of you will choose to write it in this way, which is also correct, which is going to be plus aqueous to give you Na plus aqueous plus Cl minus aqueous, which is correct as well. Okay, but what is important, okay, because we are looking into formation of bond. Okay, so you need to be very careful what kind of formation of bond that we are talking about. Okay, the formation of bond that they are talking about is going to be, if you have NaCl, they are in lattice, okay, something like this. They are in lattice, and they are forming bond, okay, with water. Okay, this water, okay, can have delta positive and delta negative. So they are called as dipole, okay, dipole. And this dipole, the water, will form bond, okay, with this ion. Like for example, you see delta negative. If you have this as sodium chloride, the positive ion will be sodium ion. They will form bonds, okay, with this Na plus. And you can see also a dipole over here. Okay, the delta plus of this hydrogen will form bond with the Cl minus. They are going to try to remove the Na plus and Cl minus apart from each other. Okay, to make them to dissolve. Okay, to make them to dissolve. So we are going to focus on this bond forming. So because of that, okay, it's a bond forming. We call it as, okay, I told you earlier in our previous lecture, okay, bond forming is exothermic. Okay, but okay, we have also, okay, we also have bond for breaking as well in within this Na plus and Cl minus. Therefore, there is possibilities of having plus and minus. What you need to remember, okay, is, okay, when they break the bond, okay, it means they are soluble. Okay, when they are soluble, whenever they are negative. But do remember, not only negative, okay, negative automatically they are soluble. Okay, but if let's say they have a small positive, so what is a small positive? Maybe +5, +7. Okay, if you notice like that, still, okay, we can consider them, okay, as being soluble as well. Okay, but if you have enthalpy of solution, okay, being positive, like for example, positive 50, positive 70. Okay, automatically it's going to be insoluble. So this is going to be an indication on, okay, if you have enthalpy of solution, yeah, how it will affect in terms of solubility of this ionic compound. Now, if you look into this checkpoint 1, okay, so if we want to write down, okay, what is going to be the equation, okay, for enthalpy change of solution of potassium sulfate, zinc chloride? I'll just show you only one. Okay, potassium sulfate, K2SO4, okay, solid ionic compound, and they are going to be added with water. You write down AQ, and you are going to get 2 moles of K plus. You will get SO4 2 minus, and they must be in aqueous. They must be in aqueous. But let's say you want to write down K2SO4 solid plus aqueous, and you want to actually write it down as K2SO4 aqueous, no problem. Both answers are accepted over here. So you can write, okay, for zinc chloride, I'm very sure you can write for zinc chloride, refer to the definition. But now, if we go into this second question, this checkpoint 1, compare the relative solubility of the following compounds. And I told you, very important, the moment you see a negative value of enthalpy of solution, that is because they are forming bonds with water. Therefore, automatically, this one is the most soluble in this particular question. Okay, so sodium bromide is the most soluble. Next, okay, if we analyze, all of them are positive. But look at the answer, okay? Like for example, the magnitude 3.9, it's a small positive. And I mentioned, if it is a small positive, they are also soluble. Therefore, sodium chloride is also soluble. That leaves us with silver chloride and silver bromide, okay, which are insoluble. There is a large positive enthalpy of solution. And this one you also should know, yeah, silver chloride, silver bromide, I think you should know silver chloride, silver bromide, silver iodide, especially the color, they are solid, okay, precipitate, okay, the white precipitate, okay, cream precipitate, okay, yellow precipitate, all these you must know, okay, you must know. Okay, but in this case, if I want to say between silver chloride and silver bromide, which one is the most insoluble? Okay, the most insoluble should be silver bromide, the most positive, okay, enthalpy change of solution. Yeah, so this one you can read. Okay, I will move on to this enthalpy change of hydration. Now, just now I gave you this diagram when you have this lattice energy. Okay, like what is lattice energy? Lattice energy is going to be when you have Na plus, which is gas. Okay, let's say you have Cl minus, which is also gas. Okay, when gases ion come in together, when they form bonds, and then when you get the NaCl solid, okay, we call that as lattice energy. This one we have learned in our previous lecture. Okay, and then, okay, I also mentioned that when you add water, okay, to this solid, when they become dissolved, okay, to separate, okay, the ion will become aqueous. Okay, when they become aqueous, this thing, okay, when you add water, this is going to be known as your enthalpy change of solution. So there should be one more enthalpy that we need to learn, okay, which is going to be the enthalpy change of hydration. What is enthalpy change of hydration? It's going to be something related with the gaseous ion, okay, to become aqueous ions. Okay, so if you look at this definition that I've written over there, enthalpy change when 1 mole of specified gaseous ion dissolve in sufficient water to form a very dilute solution. So how do I write this down? Okay, so like for example, they mentioned that it's supposed to be specified gaseous ion. Why they say specified gaseous ion? You have 2 types of gaseous ion. Okay, if let's say you're talking about NaCl. So you have Na plus ion, you have Cl minus ion. You have to do it separately. Okay, so if you add with water, okay, if I add with water, must be gases, okay, according to the definition, must be in gases, and you are going to get Na plus aqueous, Na plus aqueous. Okay, this is going to be, this one is going to be Cl minus aqueous. Okay, so this is going to be something that you need to remember, and they will form a cycle. Okay, they will form a cycle. So what is important over here? We are talking about formation of the bond between the ion and the water. Therefore, they are always bond forming. We can just simply say hydration is always going to be exothermic. Okay, so I'll just write down over here. Hydration is always going to be exothermic, and you can memorize this. Okay, solution can be positive and negative. Hydration must be always exothermic. So if you look into this checkpoint, okay, so you can see the definition and so on. If we want to compare enthalpy change of hydration between fluoride ions and iodide ions, how do we do that? Okay, how do we do that? This one, okay, recalls our lesson that we had last Monday, okay, related to your charge density. Okay, so if I have fluoride ion, so fluoride ion is going to be group 17. Okay, is quite small at the top. And then if you have this iodide ion, it's going to be at the bottom, I minus. And you can see the size is going to be more, okay, bigger, okay, because more shells, more distance. Yeah. So you can see that, okay, we have this concept as charge density, charge divided by volume. Okay, you can see that the charge, the same charge is going to be inside the smaller volume for fluoride. Therefore, you can say the charge density is going to be greater for fluoride ion. Okay, when the charge density is greater, what does it mean? If I have water, they can form a better bonding with water. If I have water over here, they don't really form a better bonding with that water. So when they form better bonding with water, it's going to be bond formation. Therefore, it's exothermic and it's going to be very much negative. Okay, it will be very much negative. This one still bond forming. Okay, but it's going to be less negative. So if I want to compare, okay, you can say that fluoride ions, okay, they will become more negative. Okay, the enthalpy change of hydration is more negative, okay, compared to iodide ions. And the same thing will apply to comment on the trend on enthalpy change of hydration down group 2 chlorides. Okay, group 2 chlorides, okay, you have magnesium, calcium, strontium, barium, all these chlorides. Okay, the same. Okay, at the top, magnesium is small. Okay, at the bottom, barium ion is going to be small. So do remember, we are talking about ions, yeah? We are not talking about the metal. Okay, so when we talk about this ion, when I have water over here, we know the charge density, the 2 plus, is going to be shared within a smaller volume. So if it is shared in a smaller volume, you are going to have a better or greater charge density. So they are going to be able to form a better bonding over here with water. Okay, they are going to be more negative. Okay, therefore, at the top is more negative, at the bottom will be less negative. So what we can say, it will become less negative as you go down. Okay, or you can say enthalpy of hydration decreases. Okay, up to you how you want to mention. Okay, or it will become less exothermic. Okay, down the group. Okay, up to you how you want to mention this. Okay, you can just go through this. Now, since just now I gave you this relationship between these three, so let's actually look into detail in a more structured way. Okay, like for example, I have Na plus gas, okay, Cl minus gas, and I am going to form NaCl, which is solid. I know this is lattice energy. Follow your definition. Yeah. And then I know when I add water, just now in the lecture, just now in the beginning, I told you when you add water, you are going to get NaCl aqueous, or you want to write down as Na plus aqueous, Cl minus aqueous. Fine, same, okay, same. But what does it mean? This is going to be your solution, enthalpy change of solution. And the last one is going to be this, from here to here. You are going to have hydration, okay, which is going to be hydration. You have two, hydration of Na plus, you must add with hydration of Cl minus because they are separate. So when you put them together, that is going to be hydration. Again, it's going to be add with Aq. And you are going to get NaCl aqueous. And you know, okay, we have learned in your AS, okay, your Hess's law, okay, you can just put it as clockwise equals to anti-clockwise, okay, depends on how you learn with your teacher. You can see lattice is clockwise. Okay, this one solution is clockwise. This is going to be anti-clockwise. So how do I write? I will write it as lattice energy plus solution equals to hydration. Okay. Now, for the beginners, okay, if you're not sure, okay, you want to memorize the formula. Okay, I come up with this helping students also. Okay, how do you memorize this formula? If you want, for the beginner, okay, okay, let your soul go. You let it go. Let the soul go. Okay, let your soul go. Negative soul. Okay, and high. So plus hydration. So you can actually have lattice energy equals to negative solution plus hydration, which is the same as lattice plus solution equals to hydration. If you want to use this formula, let your soul go and hide or something like that, up to you. But this is only for the beginners, okay? But once you become very good at it, okay, once you become very good at it, you don't need to worry about that, okay? Because, okay, we are going to look into like a situation where we are going to have, okay, let me add the page over here. We are going to have, okay, a situation where I can derive, okay, I can derive myself, okay, how am I going to write this down? Like, for example, how do I picturize or how do I visualize this, okay? So I will suggest, okay, if you want to look into this, let's say you just learn as a beginner, you know, okay, the relationship between them. But now, okay, if you have, okay, now you want to learn more in deeper content, you visualize left and right like this. Okay, I put a line over there. You always start, okay, with Na plus gas. You just put the ions in gas first, okay, at the top. Okay. To the left, okay, we always will have, okay, the gas, okay, when they form NaCl solid. This one everyone should know, this is lattice energy. Okay. And then, okay, if I add water, okay, do remember solution is not always negative, but in this case, I'm just using the solution is negative over here. I am going to add with aqueous and I'm going to get NaCl aqueous. Okay, so if I extend this line over here, I know according to the definition, okay, the gaseous ion, okay, when I add with aqueous, to give you NaCl aqueous, that is going to be your hydration. Okay, that's going to be your hydration. Now, everyone should be able to visualize this because, okay, it's very interesting because if you take a ruler and you measure this, let's say this is going to be 10 centimeter. Okay, this is 10 centimeter. And if I'm going to put another ruler over here, this is also going to be 10 centimeter. Okay, it's going to be 10 centimeter. So what does it mean? Your hydration, okay, is the same as lattice energy plus solution. Automatically, the formula comes in. Some students will ask, Mr. Gopi, how come? Okay, sometimes we do have a solution which is going to be positive. So what should we do? Okay, use the same thing. Okay, you see, I'm going to draw. You separate into two, okay, left and right. Okay, at the top, okay, let's say you have Na plus gas, Cl minus gas. Okay, you know that hydration will go down, lattice energy also will go down. So don't draw anything yet first. Okay, so now let's say I want to draw lattice energy. So I just draw lattice energy up to here. So the arrow, okay, I'll just put this one up to here. Lattice energy is what? Okay, Na plus gas, Cl minus gas, I'm going to form NaCl gas. And everyone should know now, sorry guys, okay, solid. Now, everyone should know, okay, that when I add water, okay, when I add water, I am going to get the NaCl aqueous, okay, but now we have a situation, the question was, how if it is positive? Good question. You just put another line over there at the top, and you just put NaCl aqueous. Okay, this is positive, okay, solution. And this entire thing, okay, just to make it easier for us to see, maybe we just put it at here. This is going to be lattice energy, for example. Sorry. This is lattice energy. Okay, I put it like that. Now, if the next question is when you look at the right, okay, where the arrow is supposed to end, okay, the arrow should end, okay, where, okay, this is very important. Hydration is going to form aqueous, not solid. Okay, so it's supposed to end somewhere here. Okay, supposed to end over here. Now, use the same method. Okay, I'm going to prove that the formula is going to be the same. Okay, in order to do that, okay, let's use the same thing. You put a ruler over here. This is going to be, let's say, 10 centimeter. Okay, and imagine now this is lattice energy, which is going to be 10 centimeter. Okay, and solution, okay, is going to be positive. So let's say this is negative 10. Solution is going to be positive 4, for example. Sorry, guys. Okay. Solution is going to be positive 4. Okay. So let's say I'm going to put plus 4. Okay. And when I add this together, you see here, how do I get this? Okay. Everyone should know. Okay. Everyone should know. If you have a ruler 10 centimeter and then it's going up to 4, everyone should know that this one should be 6. Okay. So it is also going down. It's supposed to be negative 6. So let's see. If I take this value negative 10, when I add with this 4, I'm going to get negative 6. What does it mean? Okay, it just means one thing, okay, which is going to be, if I have negative 6, which is going to be my hydration, if I get negative 6 because lattice energy plus with the solution, so it means that, okay, my hydration is also the same as lattice energy plus solution. So hydration equals to lat, okay, plus solution, the same thing, okay, the same thing. So you can apply that formula. So how do I actually use this formula? That is very important concept as well, okay. So now, okay, I leave it to you guys how you want to apply, which method that you want to apply, okay, to solve these kind of questions, okay. So if you want to use the formula, go ahead, use the formula, okay, but I will suggest that you try to use this method. Okay, because this is going to help you to prevent mistakes. Okay, so you can see you always start with the ion, okay, the gaseous ion, and then lattice energy is given. Write down, lattice energy is given. Hydration is all given. When you add these two hydration, you are going to get negative 912. This one is up to 902. Automatically, you know that it must be negative 10 here. Okay, that is going to be the answer. Okay, this is how you can solve this question. I want you to just go through this question as well. Okay, this question is similar with another question that I'm going to discuss after this. So I'm going to skip this part. Okay, I'm going to skip this part. Okay, but how to do is all over there. Okay, please remember this. Yeah. So examples of partial question. Okay, let's try some questions over there. Okay, what is meant by enthalpy change of hydration? You can see. Okay, it's the enthalpy change. Okay, when 1 mole of ion in the gaseous phase are dissolved in water. Okay, write an equation that represents enthalpy change of hydration in Mg2 plus ion. Okay, so if you have Mg2 plus ion, okay, make sure they are in gas plus aqueous to give you Mg2 plus aqueous. Simple as that. Suggest a reason why Mg2 plus the hydration is greater. Mg2 plus, if you compare with Ca, okay, you can see the charge density is going to be greater, okay, within the group. So because the charge density is greater, because of the size is smaller, okay, therefore they can form a better bond with the water, okay. But do remember, they want ions, okay. You don't go and tell about metals over there. We are talking about ions, okay. As long as you just say it's going to be greater charge density, you get the mark. And number 4, why it is impossible to determine enthalpy change of hydration of oxide ion. Now, what is hydration? Hydration is going to be when you add with water, okay, like for example, oxide. Okay, if I want to write the equation, O2 minus, okay, gas, when I add with water, I supposed to get, okay, this one add with water, I just normally put aqueous. I supposed to get O2 minus aqueous. But the problem is, okay, you don't get that situation because oxide ions, they will react with water. They will not dissolve only, they will react. Okay, they will react and give you the hydroxide ion. Okay, because of that, you cannot determine directly. You need to do calculation. Okay, you need to use calculation. So you cannot get this directly. So that's to answer that question. Yeah. Now, other examples, okay, we will try this example over here. Now, if I have this one related to your AS, suddenly, okay, we have formation. How to do this? Very simple. You have solid, you have aqueous. Write down magnesium chloride solid. Today I learned aqueous. It gives me MgCl aqueous. This is enthalpy change of solution. Okay, it's my enthalpy change of solution. So I want this. What is this? I want what is this according to this. Yeah, I want what is this. And then I have all this data about formation. Now, if you have studied under me, I would have told you, okay, that if you want to solve this, the easiest way is you follow the arrow like this to form MgCl. Put the arrow up, pointing up to form. To form MgCl aqueous, put the arrow pointing up. And to form 1 mole of MgCl solid, it's going to be -641. To form 1 mole of MgCl2, okay, to form 1 mole of MgCl2 aqueous is going to be -801. Now, the next step is you draw near the arrow this circle. This circle is very important. I call it a magic circle. Okay, why? Because I try to use like the arrow. You try to bend them. Okay, like bend it like Beckham or something like that. You bend it. Okay, you can see the arrow. Put it like this. Okay, the arrow, follow the circle. Follow the circle. You will notice that, okay, there are 2 arrows following the clockwise direction and 1 arrow following anti-clockwise direction. So that is going to be, okay, clockwise equals to anti-clockwise. This is going to be your Hess's law, okay? And when I add this, okay, it's going to be -641 clockwise plus enthalpy change of solution, the one that I'm looking for, equals to -801. Okay, and I can calculate my enthalpy change of solution -801 plus 641, and you will get the answer, which is going to be -160. Very simple. Yeah. And then the next one is going to be related to what we have learned today. Yeah. Okay, which is going to be, okay, I will erase this. All this, okay, I have the answers in the Google site. You can just see over there. I've written it nicely for you. Okay, so no need to actually look at my messy work over here. Okay, so here, okay, if I want to calculate the enthalpy change of hydration, how do I do? Okay, so first, like what I did, okay, you visualize left and right at the top. Okay, we are talking about MgCl2, so Mg2 plus 2Cl minus gas. Okay, and then, okay, lattice energy is given, so you write down lattice energy, so MgCl2 solid. Okay, this is going down, so that is going to be -2526. And then you have your enthalpy of solution from where you have calculated. Okay, so you put over there -160 to become MgCl2 aqueous. Okay, so what is going to happen to the right? It's supposed to come all the way here. Okay, so it's supposed to be your enthalpy of hydration. So your hydration, they only give you only one for Mg2 plus, -1890. How about the Cl minus? And you need to consider there are 2 moles. So it's supposed to be plus 2 moles. Let's say I'm just going to put X as my enthalpy change of hydration for Cl. And what is going to happen over here? This total must be the same as this total. Okay, so it's supposed to be -1890 plus 2x must be equal to -2526, okay, plus -160. If you calculate this, okay, and you divide by 2, okay, the x, you're supposed to get -398. Simple as that. Yeah, so this one is, okay, if you want, okay, to use, yeah, Mr. Gopi, I'm very weak, I don't know what's happening, use the formula. Okay, let the soul, okay, go, okay, and hide. Okay, but be very careful when you're using this formula, because for hydration, okay, you are going to have Cl2, 2Cl. Okay, you need to times by 2x. So sometimes that's why I don't encourage students, okay, to use the formula. If you're a beginner, yes, okay, maybe you can try, okay, but once you're good at it, okay, you want to minimize error, okay, use this method. Yeah, so this is going to be another one part over here, example of one past year question. Okay, but I'm not going to discuss this because, okay, this part, okay, related to solubility of sulfate, explaining and so on, has been removed to chapter 27 in your new syllabus. Okay, it's part of the question, but I just put it over here. For those very good students, you want to learn, you can refer to the marking key. Mr. Gopi, I still couldn't understand. You just use this one. Okay, I have actually discussed about this, okay, in my YouTube video. You can just click over there, you can learn. Yeah. But okay, we will treat this like a back to the future movie. You know, suddenly after chapter 27, yeah, we are going to, I just say, remember last time in lecture 2, okay, I put over here, yeah, we are going to discuss about it. So I will come back to this again. Yeah, so this one, for those good students, you want to go through that, okay, go ahead. Yeah, go ahead. Okay, now, so the second part, okay, is going to be entropy. I hope you guys are still with me. Okay, I know it's going to be very fast. Okay, I know also because I'm going very fast also. Okay, but okay, we try to cover as much as possible so that it's beneficial for everyone. Yeah, beneficial for everyone. You still have problem to follow? Repeat this video again, watch it again, up to you. You want a slower pace? Go and look for another video, okay, in the site. Okay, it is there. Okay, so some of you maybe, okay, your teacher would maybe didn't enter the entropy part. Okay, I will try to go as clear as possible. Okay, now what is entropy? Okay, most of you wouldn't have heard about entropy before. Okay, but it's a simple concept. It's a measure of number of possible arrangement of particles and their energies or the disorder of the system. Okay, just take it in this way. Okay, if I enter a class and the class, everyone is fighting with each other, everyone pulling their hairs, each other's hair. It's very chaotic. Okay, that is what we call as disorder. Okay, disorder. But if I enter a class, everyone is seated, ready to learn. Yeah, so that is going to be ordered. Okay, of course, for teaching, we want something that is ordered. Okay, but for chemistry, we want them to be disordered. Why? I want everything to be moving. I want everything to be chaotic because then only the reaction can happen. Okay, so entropy, if you want to put it in a simple term, entropy is going to be a measure of randomness, okay, or measure of randomness or disorder, okay, or disorder. So do remember this one, okay. Some students will get confused, okay. Is it going to be always positive? Is it going to be negative and so on? My answer is going to be quite simple. If entropy alone, the answer is going to be it's always positive. If entropy alone. But if you're talking about entropy change, then okay, it can be positive, it can be negative. Later, we will discuss about entropy change. Okay, of course, it will be past and present. So there will be some sort of a change. Okay, if there is a decrease in entropy, then it's negative. There's going to be increase in entropy, then it's going to be positive. Okay, so we will discuss about this further. Okay, so entropy alone is positive. If I'm looking at entropy change, this triangle is change. Okay, it can be either positive or negative. Yeah, so let's compare. Okay, so when we compare entropy values, first of all, okay, look at the part that I circle over here. Calcium, solid, bromine, liquid, ammonia gas. What can you see? You can see 41.4, 151, 192. You can generally see that, okay, your entropy for gas is generally higher compared to liquid, compared to solid. So this is going to be the first point that you need to take note, which is going to be generally gases have higher entropy. Why? Because they are more random. Okay, they are more disordered compared to liquid, compared to solid. Okay, solid will have a regular arrangement. They are ordered. Okay, so they don't have a lot of entropy. So that is general, but there are exceptions. You can read on yourself. Okay, there are exceptions, but generally, yeah, generally. So if you look at the second part, if I want to compare, if let's say I have the same state, solid and solid, and I have calcium oxide, which is CaO, and calcium carbonate, you can see that, okay, CaO is more simple. Why? Why more simple? 2 atoms only, calcium and oxygen. Okay, this one is a bit more complex. Why? Because 1, 2, and another 3, which is going to be 5 atoms. Okay, so the complex molecules, okay, will have 5 atoms. The arrangement, the randomness that they can create is more compared to the randomness that calcium oxide can create. Therefore, okay, complex molecule will have higher entropy over simple molecules. Therefore, you can see that calcium carbonate have higher entropy compared to calcium oxide. This will also apply for carbon monoxide. You see carbon monoxide, carbon dioxide. Carbon dioxide is going to be higher. Okay, so this is going to be another comparison. Next comparison is going to be, I selected diamond and graphite. Diamond and graphite, okay, if you look into which substance is hard, okay, of course, diamond. Why it is hard? Because it's going to be arranged in a regular arrangement. The atoms of carbon, they are going to be arranged in a regular arrangement. This one are electrodes, okay, same carbon atoms are building them, okay, but graphite, they have layers. They can slide on top of each other. Because of that, they are going to be soft, okay. So because of diamond having a much more harder state, okay, which is going to be because it's more regularly arranged, okay, therefore the entropy is going to be more ordered. More ordered, it means the entropy is less, okay, you can see that. Okay, this is going to be less ordered, so therefore you can have 5.7. Yeah, so that's going to be another part. So let's move on to the fourth part. Okay, the fourth part is going to be quite simple. If you just simply look at it, ice is going to be solid, water is going to be liquid, okay, steam is going to be gas. Okay, of course, just now in the first situation, I already told you, gas will have higher entropy than liquid than solid. Okay, fine. Okay, but okay, what I want to tell over here is this water, okay, in terms of ice, water, and steam, they can be changed from ice to steam, okay, ice to liquid, okay, to become steam because of the increase in temperature. When you supply heat, okay, what happens? They are going to have, okay, from the regular arrangement, they are going to start to slide, start to rotate, and then they are going to break free. They are going to become liquid. Then after that, they become gas. They're able to move everywhere that they like. Okay, because of that, okay, you can come into this conclusion. When temperature increases, okay, your entropy also will increase gradually. Okay, gradually. Okay, except, okay, when you reach at melting point and boiling point, the entropy will suddenly shoot up. Okay, you can see here, okay, and you can see here the same graph actually, okay, but what I want to highlight over here is, okay, this is going to be temperature in Kelvin, okay, so sometimes, okay, they will ask you to sketch this graph. Be very careful. Melting point is 0 degrees, 100 degrees is going to be boiling point. This is Kelvin, so this one you have to add 273. At 273. So if they ask you melting point, this one supposed to be 273. This one supposed to be at 373. Don't go put 100. Don't go put 0. Yeah. Later I'll show you one example later. Yeah. There is one question that they have asked before. Yeah. In your past year paper. Next checkpoint. Yeah. Now explain the difference in entropy in each of the following pairs. You can differentiate them. How? You see, liquid, look at the state first, okay? Liquid, solid. Automatically, liquid will have higher entropy. No need to think about it, okay? Why? Okay, they are going to be able to rotate, slide over, you can read, okay, on your own. Okay, the second one, you see gas and gas, okay? Then you have to look into different ways to differentiate them. H2 and CH4, this is more complex, more arrangement. Okay, so of course, CH4 will have higher entropy. You explain, it's all over there. Okay, liquid and solid. Of course, liquid will have higher entropy. Okay, and then you can see, first look at the state, gas and liquid. Gas will have higher. Okay, but some of you will ask, Mr. Gopi, don't you think SO3 is more complex compared to SO2? Yes, I think so. Okay, but the priority is given, okay, to the state. Okay, when you have gas, they are able to move around. When you have liquid, okay, even though they have different probability, there are going to be more arrangement, but they can only slide, they can only rotate around that area only. So they are not that disordered compared to the gas. So you can read all this, is explained clearly over there. So sometimes, just now I mentioned about, okay, we need to look into why entropy change, okay, can be positive, why they can be negative. It's because of this. Just now we just compare between this and that. Okay, but if you are having any reaction, we can predict, okay, whether entropy is going to be increasing or decreasing. How do we predict? The answer is gas molecules. I want you to remember, I can mention it 3 times. Gas molecules, gas molecules, gas molecules. Please remember this. You are looking into gas molecules, not solid, not liquid. Okay, I will teach you here. You see, there is no gas molecule, put 0. No gas molecule, 1 mole, put 1. From here to here, okay, there is going to be increase in entropy, okay, because no gas, there is 1 mole of gas, okay, increase in entropy. If you look over here, gas, 2 moles, total 5 moles, 2 gas molecule to give you 5 moles of gas molecule, increase in entropy. So your entropy will be positive, entropy will be positive. Okay, but the your entropy change, yeah, please remember entropy change. Now this entropy change, okay, you can see here it's going to be 3 plus 1, 4 and 2, 4 to 2. Okay, from 4 moles of gas, now you have 2 moles of gas. Now it's going to be decreasing. Okay, therefore your entropy change is going to be negative. Okay, because less gas molecules being produced. Okay, so it means that they are going to become more ordered. Okay, so I hope you can understand this. Yeah, so I'll just move on. Okay, so here, okay, if you want to suggest and so on, please go through this yourself. Okay, like for example, you see here gas, I'll just go through 1, 2 moles to 0, decrease. Yeah, you can see decrease. And you can say the reactant is going to have more entropy than the product and so on. Okay, please go through all this. Now I will go through the one that we need to calculate. I think some students, they are very poor in calculation. Okay, if you are very poor in calculation, please take that this change in the new syllabus is something that is going to help you because they have removed a lot of calculations. Okay, they have removed a lot of calculations and they want you to only focus on here. Yeah, enthalpy of system equals to product minus reactant. Yeah, so if you are not sure, okay, please refer to the syllabus. Yeah, I have put in the Google site as well. Check, okay, whenever you learn. Even the new syllabus textbook, okay, and the old syllabus textbook, they have all the same examples over there. So some of the examples, they are not needed. Okay, so you plan, okay, you plan accordingly. But if you want to calculate, okay, the enthalpy change, the entropy change, it's supposed to be product minus reactant. I'll show you how to use this formula. Okay, let's say, for example, we have this situation. Okay, from here to here, I want to calculate, okay, the entropy change of the system. The formula is going to be given over there, product minus reactant. How do we do this? Product, 2 moles of CaO. They are giving you this 2 times, okay, 2 times 39.7. That's your product minus the reactant 2Ca. Okay, 2Ca, 2 times 41.4. Okay, and then you plus with oxygen. Oxygen is 205. Okay, product minus the reactant. You calculate. Okay, and you should be able to get this value, negative 208.4. Very simple. Okay, product minus the reactant. What you need to take note, what you need to be very careful is this number, these 2 and these 2, because you need to take into account the stoichiometry of the equation. Okay, something like when we did for our enthalpy calculations, you must be very careful with this. Yeah, so this one also the same. Okay, you can try on your own. Answer is given. Okay, even this one as well. Okay, same. You try. Okay, all the answers are given. Okay, I think for this one, I think one of the information is missing. Okay, H2O gas. Okay, is missing. Okay, if you want the detail for that, what is this value that is missing? You refer to the answer key for this lecture note. Okay, I have written it over there. Okay, but all the working and so on, don't worry, Mr. Gopi, skip everything. I don't understand. Every working, okay, is for this are inside my slide, the answer key, and the working for this also there. I didn't check the working whether it's correct or not, but if you notice anything that is wrong and so on, you adjust accordingly. But the one that I thought, okay, is going to be correct. This one is taken from the textbook CD only last time, yeah. But so far, I think it's correct, yeah. Now, So let's actually try some question. How will they ask this, okay, in the actual situation? Okay, like for example, now I have silicon tetrachloride prepared using this equation and so on. They give you entropy change. Okay, how do I calculate entropy of chlorine? Very simple. Yeah, this one is going to be entropy of the system. Okay, so I just don't want to write everything. Also can 2 to 5.7 equals to, okay, your product. Okay, this is product SiCl4 is given 239. Okay, minus the reactant. So reactant Si, okay, 18.7 is given. Okay, plus 2 times, okay, and then I need to find the entropy, okay, of the chlorine. So I just 2 times like this, okay. So you just try to calculate. If I bring this to the left, maybe I'll have 18.7, okay, plus 2 entropy equals to 239 plus 225. So you just calculate, okay, this one, when you add, okay, you add again 18.7, then divide everything by 2, okay. So once you do that, okay, you will get the answer. So make sure you get the answer 223. Okay, if you want a better working, yes, yeah, thank you, Christopher. Okay, if you want a better working, okay, you can actually look at the answer key that I prepared. Yeah. Now next, explain why entropy change of reaction 1 is negative. Yeah. So why is negative? Very simple. Yeah. Remember just now I mentioned it 3 times. Okay, I can actually mention it 4 times now. We always look at the gas. Okay, look at the gas. So it's 2 moles, no gas, 0. 2 to become 0. Okay, there is going to be less molecules of gas that is going to be formed. Okay, because of that, okay, the entropy is going to decrease. Okay, because of that, the entropy change is going to be negative. Okay, that's why I told you entropy itself is always positive. Entropy change can be positive, can be negative. Okay, I hope you get what I'm trying to teach. Now, just now I also mentioned about, I will discuss about the graph. Okay, you can see, assume the entropy of S for water is 0 at 0 Kelvin, 0. Okay, fine. Sketch a graph to show how entropy changes for water, because from 0 to 300. We have learned that when you compare, okay, your entropy increases gradually up to melting point and boiling point. Now, this is going to melt at 0 degrees Celsius. Okay, it's going to boil at 100 degrees Celsius. If I add 273, this is going to be 273 Kelvin. This is going to be 373 Kelvin. I'm not going to bother about this because it's outside of the scale that is given. So I need to be very careful about 273. So 273 is somewhere here. And it starts from 0. Okay, so how do I draw this? How do I sketch this graph? Gradual increase, sudden increase, go like this. Okay, just simple like that. Okay, so this is going to be gradual increase of entropy, sudden increase, then it will continue. Okay, up to where? Okay, up to 373. Okay, if you have 373 here, then there's going to be another going up, then go. Okay, you can refer to the diagram that I've given to you earlier. Yeah. Now, place one tick, okay, in each of the row. Okay, if I want to place a tick, solid dissolve in water. Okay, you see, solid is already like solid. They cannot move. Okay, they are regular, and then I put water, they dissolve. Okay, of course, the S is going to be positive. It will become more disordered. And if I have water, okay, water boiling to steam, liquid to become gas. Okay, of course, we want from a liquid, okay, they are just able to rotate and slide, and now suddenly they can move around. Okay, so it's going to be, S is going to be positive as well. Okay, you can check all this. Okay, this is all this I have done. Okay, I hope you really can understand this. Okay, now I'll see the chat. Okay, so far everything is good. Okay, I'll pass to you as always. Okay, currently my Padlet is not working. Okay, I think because of the connection, but I will start a live quiz now, the quizzes. Okay, and then I'll pass you the link, and then you can just join the quizzes. Okay, just give me a moment. So this quiz, I think quite simple, seven questions only. Okay, so I'll put it in the chat. Okay, you can just join. Okay, but I will start after 1 minute. Yeah, I will not wait for everyone. Okay, it's better if you name it according to your campus, your results, and so on. We can actually see whether you can understand and so on. Yeah. Okay, but of course, okay, if you guys have questions and so on, okay, feel free. Okay, you have my number as usual over there. Feel free to ask me. You can ask your teacher for clarifications and so on. Okay, the thing is, we want to learn everything together. Yeah, so if you find that it's going to be too fast, which I do agree, I'm not going to say it's too slow. Yeah, it is very fast. Okay, but it's supposed to be done after one lesson. Yeah, so it doesn't like it's a review. Okay, so the video, okay, is there in the slide. Okay, if you have been once, I think you know what I usually do. Okay, you can just go and use that. Okay, it's everything is updated. Okay, every day, I think. Okay, so if you want to go and see, everything is there. Okay, so you can use that. Okay, now I think I will not wait further. Okay, I'll just start. Yeah. Okay, for those who are doing, okay, continue. And then for those who have completed, you can just listen to me, yeah. So maybe I'll just go through some of the questions over here. Okay, so you can see 20 incorrect and so on, just go through. Enthalpy of solution is always exothermic. The answer is false, okay. Enthalpy of solution can be positive, can be also negative, okay. But okay, if it is negative, automatically they're soluble, or small positive, they're soluble, yeah. So this one is okay. Maybe number 3, 20 incorrect. Okay, enthalpy change of hydration is always endothermic. Okay, enthalpy change of hydration is always exothermic. Okay, please remember that. Even this one, which relationship is correct? Okay, let your soul go and hide. Yeah, so or okay, if you know the enthalpy change of hydration equals to lattice energy plus solution. Yeah, so this one just now I explained. Okay, it's okay, understandable. Okay, so what is entropy? Measure of randomness. Okay, which one will have higher entropy? I think this one, most of you got it correct. So 14, which formula is correct for the entropy of the system? Very simple. It's supposed to be product minus the reactant. So those 15 students got it incorrect. Okay, please take note. Products minus the reactant. And this one, okay, I think this one is important. Okay, because I don't have Padlet for today. Okay, so your comments will help me, okay, to improve my lesson in future. Yeah. So please, okay, work together with your teachers. Okay, if there is another any parts that I've mentioned over here not so clear and so on. Okay, please also talk to your teacher, and then they can also help you. Yeah, all my materials have been already uploaded. Okay, in Google site. Okay, I've shared it to your teachers as well. You can get it there. The video recording after this, I will share it to your teachers as well. Okay, you can watch it again. And quizzes. Okay, if you want to try the same quizzes, you feel you want to try again. Yeah, I'll pass you another link. Okay, through the site, you can actually try that quizzes. Okay, that's all for today. Okay, thank you guys. Okay, bye.